Hello, everybody. So I will talk about the educational opportunities with MEG at the Qualcomm Institute. Ramesh brought together the clinical team led by Dr. Li and Huang with the engineers at QI, in particular my colleague Gans and me. QI has an internship program, which is called mHealth Workforce Initiative. It's led by Gans, and it has 1 to 2 years internship for undergraduate students who are designing and developing real-world applications in healthcare. So this program is really very valuable. It gives them an advantage in future graduate studies or in future job placement because it gives them the experience like working in, having 1 or 2 years experience in a workplace. We've had 3 students working on MEG this year, so they've been working for 1 year on machine learning models. We actually have more students that come and go, but these have been considered as interns, and we also have volunteers from outside the campus. The students are working on 2 use cases on analyzing MEG data. The first one is detecting epileptic spikes from MEG scans. Currently, this is a manual process where a very specialized analyst manually inspects all the scans, and it takes about 10 to 20 hours for 1 hour recording for a patient. It's not trivial because scans can have many, many spikes, and not all of them are epileptic spikes. So it's a very time-consuming process, and it's the bottleneck in the clinical care. It's really the data analysis. It's not in the data acquisition where you could scan several patients during a day, but then you have to wait for somebody to analyze the data in order to make clinical decisions. The students are developing a neural network model that automates the spike detection process. So this can really have an impact in speeding up the clinical workflow. Another use case is detecting post-traumatic stress disorder, or PTSD, or traumatic brain injury from ECG or MEG scans. The students are developing machine learning models that can classify a scan if it's healthy control or PTSD or TBI. They are currently working on ECG scans and not MEG for this use case because of the limitation of the IRB protocol. So all this is human subject data. So we are subject with the IRB protocols that we have in place, and the data has to be de-identified before being uploaded to the cloud. So the first use case, which is on epilepsy spike detection, the clinical team, led by Dr. Li and Huang, they have about 1,000 cases of MEG scans. So this is a very valuable database, probably the best in the world. And so the possibility for data analysis are huge here. The MEG scans have 306 channels divided in 8 areas of the brain. Concurrently with MEG, all the recordings have also EEG and ECG for heartbeat and EOG for eyes. Now, what's the traditional approaches? So the state-of-the-art in machine learning or the data analysis for spike detection is based on EEG data. And that's because most hospitals have EEG machines, but very few have MEG machines. Now, EEG can be very good at detecting if there is a spike or not, but it's not very good at localizing. And that's very important for surgeons in order to really go and remove the right area of the brain. So the students are developing neural networks that automate the spike detection based on MEG data. They start with the MEG data, and then later we want to combine the MEG data with all the other data streams that are collected just to improve performance. Their approach is to use neural networks, so CNNs, and they build CNNs for every channel, and then they also build them for multi-channel representation. And that's because epileptic spikes don't occur in isolation just in one channel. So you need to account for all the surrounding areas and the dependencies between them. The early results from their model is about 92% accuracy in detecting if there is a spike and where it is. So this is very promising for speeding up the process. The other use case that the students have been working on is detecting PTSD and TBI from ECG data. So why ECG? Because heart rate variability comes from ECG recordings, which have one channel for heartbeat. We have a very good hypothesis for PTSD because healthy people have more variable heart rate, while PTSD patients, they have low variability. So heart rate is more stable. So then it's easier to distinguish for PTSD if they have it or not. But for TBI, it's more challenging. We don't have a good hypothesis for that. Some people, their ECG recording look like normal people, while some look like PTSD. So we actually expect new insights from machine learning in order to distinguish between TBI and the others. The traditional approaches for detecting PTSD is based on unsupervised learning and feature extractions, for example, like wavelet scattering or time frequency analysis. But instead, the students are doing machine learning, they're doing neural networks, in particular a CNN combined with an SVM, which is support vector machines, so combined architecture to improve accuracy. Their current accuracy in distinguishing between PTSD and control is like 85% in an original test case they had for training, and then 75% in a totally new unseen set. Although like these numbers seem lower than for 92% accuracy for epileptic use case, these are still higher than the standard state of the art. So they look promising, and they are working on improving them. Now, I won't talk too much about this diagram. It's too detailed, but just as a high level, our effort research with MEG is part of a bigger vision in QI of data sharing and analysis and doing collaborative machine learning in the cloud, in this case in AWS. So we are working on an architecture where, for example, we distinguish between data producers and data consumers. In this case, there is an account in AWS for MEG data, where the clinical team can upload all their MEG recording, let's say 1,000 patients, and then there is a separate account for data consumers, in this case the students who are analyzing the data. And according to policies, we can decide what data the students can have access to, and it separates the ownership and the restrictions between the data producers and data consumers. Because the ultimate goal, what we have is data sharing and collaboration and allowing for more researchers to access the data and produce insights. Thank you.